have your solutions here for this one. Just kidding, I'm kind of picking on Sage for this.
I like it.
So I've given us a small molecule. And hopefully you guys see the connection. This question, how many ways can you draw C3H7N? You could do some guess and check, but there is a tool we learned right at the end of yesterday's class that will give us an idea of what is allowed and what is maybe not allowed. What types of things should we look for? What would be a good first step?
2 chickens.
2 chicken rule. Our degrees of unsaturation will be twice the number of carbons, less the number of hydrogens. There are no halogens, plus 1 hydrogen, plus 1 nitrogen, plus 2 divided by 2. Starts with 2, ends with 2, divides by 2, 2 additions, 2 subtractions. So that's 6, minus 7 is -1, plus 1 is 0, plus 2 is 2, divided by 2. This is 1 degree of unsaturation. So all of the structures you show, they have at least 1 alkene. Is that correct? Every structure has an alkene. Could have a ring. So an alkene is far too specific of a functional group that has to be there. Rings and pi bonds give us degrees of unsaturation. But does the double bond have to be between carbons? Could be a carbon-nitrogen double bond as well in there. That would make it an imine instead of an amine. So there are a lot of different functional groups that could show up with this one chemical formula. Did anybody come up with one that they want to add to the board? Aiden? Anybody else? I can think of at least 4 different ways, maybe 5. Very close, but you do have to show that hydrogen.
Oh.
You don't have to show the bond. Yep. Yeah, go ahead, add it up. Too many degrees of unsaturation.
Oh, yeah, I kind of forgot what degrees of unsaturation were.
It's 1 pi bond, or it's 1 ring. You have an alkyl, or
It's got to be a cycle.
doesn't have to be a cyclic structure, but it can't have 2 pi bonds like what you have. Yes, that is perfect. Anybody else have one they want to show? Good. Too many degrees of unsaturation, Hayden.
I need to study that.
Why does this have too many degrees of unsaturation? A ring and, not an alkene, because it's a carbon-nitrogen double bond, but it has a ring and a pi bond. That's 2 degrees of unsaturation. That's not an impossible structure, but if we look at the number of hydrogens, 2, 4, 5, doesn't match our chemical formula.
Oh, I forgot the triangle.
If you change this to this compound, which you then have to add NH2, that's a reasonable structure. With this one up here, I'm just going to extend the double bond to make it a little bit more clear that it's the carbon to nitrogen double bond. With the double bond only taking up like half of the single bond length, it kind of looked like there might be other atoms in there, so I just wanted to clarify that. You can also clarify it a little bit more by connecting this single bond all the way across. I know double bonds sometimes confuse people, so do your best to make it as least confusing as possible. Now, these two structures here, they both have a pi bond. And we could say that the nitrogen is in the same place. The nitrogen is on one of the end carbons, which means that the pi bond is just being relocated. There's another way that we could have this nitrogen on the end carbon and have the pi bond in another position. And then there's just one version for us to have the nitrogen coming off of the center position rather than one of the terminal positions. And it doesn't matter which side the pi bond goes onto, it would be the same structure. We have a cyclopropane with an amine coming off of it, and here we have what's referred to as an N-heterocyclic structure. It's a cyclic molecule, but it's a heterocyclic, specifically with nitrogen.
Could you please explain that formula one time? Like the inputs?
Yeah. This is chicken. C, H, halogens, nitrogens. When a nitrogen is in an organic molecule, it brings with it one more hydrogen than you would anticipate if there were no nitrogens. When you have a halogen, it takes the place of a hydrogen. So a fully saturated organic molecule, a fully saturated hydrocarbon, would have the chemical formula CnH2n plus 2. 2n plus 2. So if this molecule was just a fully saturated hydrocarbon, 2n minus the number of H plus 2 would be 0. Remember that a cycloalkane is CnH2n. It loses that 2, which means now you would have 1 degree of unsaturation. But placing these heteroatoms, the halogen and the nitrogen, halogens take the place of hydrogens. Nitrogens typically bring an additional hydrogen with them. So the formula accounts for that. Oxygens don't substitute a hydrogen or bring an additional hydrogen. They preserve the chemical formula. So oxygen doesn't show up in here. Are there other ways that you guys could see a molecule being drawn for this? How about a 3-membered ring that includes the nitrogen and then has a methyl group coming off of it? And then lastly, what about nitrogen attached to the center of the 3 carbons, but attached with a double bond? I wanted to give you guys a small molecule. Look at how many different ways that small chemical formula can show up. How would you know which of those molecules you're dealing with? If I tell you that you have C3H7N, what structure do you have? That's where we're headed with this unit, with using instrumentation to get us information about this molecule. Not this molecule, a molecule. All right, we're going to start with mass spec, which actually is going to be the least useful in helping us answer this question, because mass spec gives us molecular weight, which may or may not be useful for the chemical formula, and sometimes molecular fragments. So we'll look at what those fragments look like. Throughout this unit, I'm going to be referencing a website pretty frequently. If you scroll down on our homepage, all the way down to the Japanese spectral database, otherwise called SDBS, which I think is maybe spectral database. I'm not quite sure. This website has, I'm not actually sure, hundreds of thousands of molecules, maybe more. And you can look up almost anything. It is surprising they don't have a lot of small molecules, but they have a ton of very large molecules. So for this, I want to look at a compound called benzyl bromide. You have to scroll down to the bottom and hit this search button. You guys can see there's a lot of other ways to search for molecules there. They'll give me compounds that are similar, even if they're not exactly what I'm looking for. Oddly enough, this is what I searched, and it didn't give it to me right away. And then across here, you can see molecular weight and several different types of spectroscopy: mass spec, carbon NMR, proton NMR, IR, Raman, and ESR. So I want to look at the mass spectrum. You'll notice on this database, they don't have every spectrum for every compound. But they generally have a lot. This is a mass spectrum. Do you guys know the plural of spectrum? Spectra. Yeah. So this mass spectrum, we'll start by analyzing the axes. Along the y-axis, we have relative intensity. So basically, abundance. How much each signal along the x-axis is present. If we created a spectrum along our x-axis of people who are 5'8" in this classroom, and 5'9" and 5'7", and all of the different heights, then we would be seeing abundance of people that have that specific height, a relative intensity. That's really all we're looking at there. Along the x-axis is mass to charge, given with units m per z. And the mass is atomic mass units. It's very important here to remember that atomic mass units differentiate isotopes from each other. The H1 isotope, one proton in the nucleus for hydrogen, no neutrons, has a different mass number than deuterium, the H2 isotope, one proton and one neutron. They have different mass units. If they were detected here, they would show up at different places. You got a question?
Yeah, so wasn't this in nuclear agenda?
Wasn't this what?
Isn't MC nuclear chemistry?
I mean, you are looking at a mass, and the mass is decided by how heavy the nucleus is.
Right. So we're going to be like primarily doing it with like graph interpretation, or they're going to be like mental calculations with the NC.
Do you know what? I have a lot of students that always ask, can I bring a calculator to the midterm, to the final, because of this? And you can. It's not usually necessary. So there's a lot of information we'll be able to pull out, but there is some calculations. We'll look at some of the most common calculations anyways. We're looking at mass to charge. This tells us something very important. Charged particles reach a detector. This instrument will only be able to pick up signals if that particle is charged. Then it can map out the mass to that charge. And almost always, the charge that the particle will have is a +1 charge. That's what we look at most often, a particle with a +1 charge. How vague is particle, by the way? Very vague. So, am I suggesting that we can measure the mass of individual pieces of a molecule all the way down to their atomic mass units? Does this instrument have a scale, a balance, that we put a particle on and we can adjust its mass? Definitely not. That would be crazy. So how does this instrument work then? Let's look at the setup for the instrument. There are different types of mass spectrometers, but the one that I want to walk you guys through has this kind of 90-degree bend to it. On the left-hand side here, we're going to have sample input. There are different ways to get your sample into a mass spectrometer. In our organic chemistry lab, so those of you that are joining me this afternoon in lab, we have a giant GC-MS. It's a gas chromatogram followed by a mass spectrometer. So that separates compounds in a mixture by GC, and then it puts it into the mass spec. There are also liquid chromatograms that separate in the liquid phase rather than gas. Either way, once the sample gets in here, it's usually aerosolized, it's gaseous, it's a vapor, and this sample gets bombarded by an electron beam. I want you guys to think of that electron beam like a laser, and that laser is picking off electrons from the molecules that it hits. So my sample is going to lose an electron from this. And I know that feels weird, like shouldn't the electron beam be adding electrons to a molecule? But again, I want you to think of this, maybe a laser is not a good idea, but a BB gun, some sort of rifle that is picking off electrons from the molecule. Generally, that creates two things. It creates a cation. Oh, I'm going to do that in green. Because one electron has been removed, if you take out a negative charge, you'll leave behind a positive. And it forms a radical. Because if you pick off one electron, you're picking off somebody's pair, and the other radical is, the other electron is left behind, an unpaired radical. So your sample gets input, you generate a cation and a radical from this electron beam, and then that cation and radical are subjected to a magnetic field. And I'm going to show this magnetic field kind of bending along this 90-degree turn. My arrows are doing a very bad job of showing that this magnetic field is pointing along this turn. The magnetic field is only going to interact with charged particles. It has no interaction with electrons. Or excuse me, it has no interaction with unpaired electrons. So this radical component is unaffected by the magnetic field, and this whole instrument is typically done under vacuum. The analysis is done under vacuum, so those radicals just get sucked into a waste with the vacuum. But the cation is subjected to the magnetic field. And depending on how heavy that cation is, determines how much it will interact with the magnetic field before it gets down here to the detector. if the part of the molecule is very small, doesn't weigh very much, and has a positive charge, it's affected by the magnetic field very strongly. If the part of the molecule is large, has a large mass with just one positive charge, it's affected by the magnetic field very weakly. So light mass fragments are pulled strongly, and heavy mass fragments are pulled less strongly, and they hit the detector at different places. So how does the instrument know the atomic mass units if it's not taking a little tiny scale and weighing the exact mass of every fragment? It's making this prediction based on how strong the magnetic field is and where the particle is hitting the detector. Other instrumentations vary the magnetic field, and they've got just one detector. Depending on what hits the detector when the magnetic field is at different strengths is how the instrument knows how heavy the particle is. Andrina, you had a question?
I was just wanting to make sure the radical will go to the waste, but then the cation will either go to light mass or heavy mass.
That's right. Yeah. Sorry, that wasn't super clear. And there are instances where the radical and the cation are still joined on the same molecule. So the radical is not being pulled to the detector. The cation is, but the radical is getting pulled along for the ride. Any questions on that instrumentation setup? How many molecules do you think we'll analyze with that sample input? I'll give you a hint. It's a small number. 2 molecules. No, sorry. I said small for organic chemistry, small for chemistry. Do you think we put in a mole's worth of molecules? 6.022 times 10 to the 23rd? No, that would be a lot. Remember, this is being done under vacuum, and we're putting in a gaseous amount of or a compound in a gaseous phase, so it's a very small amount. We're putting in maybe like 500 million molecules, a very small number of molecules. You guys would agree that's a small number, right? Like say 500 million, 5 times 10 to the 8th. Convert that into moles. How many moles is that? That's like 1 times 10 to the negative 15th moles. Would you agree now that that is a tiny number of molecules? You can't weigh that on a balance in our chemistry labs. That doesn't weigh enough, unless you have a very heavy molecule. We're taking a very small number, just a few 100 million molecules. Anybody take statistics yet? Is that a good sample size? Like if you're gonna analyze a molecule and you're trying to avoid error, what's the smallest sample size you want to go for statistics? 30. So if you analyze 500 million molecules, is that a good sample size? Yes, that's great. Like the more the better, right? Because you are looking at repeated results. This is the spectrum that's generated. After 500 million molecules are blasted in that electron beam, they can form a radical and a cation in any number of ways. This is the spectrum that's generated. And because you're analyzing so many molecules, this spectrum is constant for every molecule. Not to say that this is the spectrum for every molecule, but every time you analyze the same sample, you get the same mass spectrum. Those molecules are always going to break in the same ways so that you get all of these signals at the same masses with the same relative intensities. This mass spectrum was generated after 500 million molecules were blasted. Very few of them kept this high molecular mass. Almost all of them had this specific molecular mass, and then a few of these. Now you go into a lab, you put an unknown sample into a mass spec, you're going to get that same mass spectrum with the same signals at the same masses with the same relative intensities, because you have done very good statistics and you said even after 500 million molecules, this is the pattern that we see. You guys get an idea of how we form this? Now we want to analyze this. We want to look more at what this tells us.
You said the detector determines the weight by where the particle hits and what?
Or how strong the magnetic field is.
Oh, okay.
Some of these instruments are linear, they're not bent. And so the magnetic field will kind of increase in strength, and that's going to cause different fragments to be pulled towards the detector at a different time. To me, this instrumentation makes more sense. If you are somebody who needs to build instruments, then you would learn more about this. But for a first glance at how an instrument is able to distinguish different masses from each other, I think this 90-degree bend makes more sense. All right. One of our most important signals is called the molecular ion signal. Like the name suggests, this molecular ion has the mass of the molecule. Nothing has been lost. And yet, it has a positive charge. This is produced by a radical cation. It is the whole molecule. Now I'm going to draw for you guys benzyl bromide, and we're going to look at a few different ways that benzyl bromide can be turned into a molecular ion. So benzyl bromide, that's a C6H5 CH2Br. One of the best places to remove one electron in order to form a molecular ion, in order to form a radical cation, is to remove an electron from a pi bond. There are a lot of pi bonds in benzene. Well, I guess 3 pi bonds in benzene. This applies to any pi bond, by the way. It does not have to be an aromatic pi bond, an alkene pi bond, an alkyne pi bond, carbonyl pi bond. Any pi bond can easily lose an electron. So, would you guys agree, it doesn't matter which of these 3 I choose, I'm just going to choose one of them. I'm going to choose this one down here. When one of those electrons is removed, the other electron is left behind. One of the carbons is going to lose both of those electrons. One of the carbons is going to lose only one of them. Once again, it doesn't matter which one does what in this case. So I'm going to say the positive charge forms on this carbon and the radical forms on this carbon could have been swapped, but I have taken 2 pi electrons, I have removed one of them. That leaves behind a positive, because I've removed a negative particle, and it leaves behind an unpaired electron. You guys comfortable with this? Now this is a cation. It's a radical cation, but the cation is pulled by the magnetic field, and it hits the detector. So where does it hit the detector? Well, it's got a formula of C7, H7, Br. So I could go to my periodic table, could do the math to add that up. 12 times 7, 84, plus 7, 91, plus bromine. Now if you look at bromine's mass on the periodic table, it will tell you 79.9. But bromine does not weigh 79.9. Bromine weighs 79, 51% of the time, and 81, 49% of the time. If you had 100 atoms of bromine, 51 of them would weigh 79, 49 of them would weigh 81. So bromine does not weigh 79.9, bromine weighs 79 and 81. So when I do 91 plus 79, 170. Or 91 plus 81, which should be 172. And now we look at our mass spectrum. Look at these two signals. That's 170, and that's 172. I don't get a signal at 171. If you had actually used the values from the periodic table, you would have gotten something close to 171. I don't have a signal at 171. That's because there is no bromine on a molecule that has that mass. Bromine has a mass of 79 or a mass of 81. We're going to come back to this, but I'm pointing it out. So this molecule technically has 2 molecular ions, depending on which isotope of bromine is added in. But if you look, SDBS will always tell you that the lower isotopic mass is the molecular ion. When I give you mass spec signals, I will analyze these numbers for you so that you don't have to guess, and I will only give the lower molecular ion as well. So we're going to say here that the signal that this hits will be 170 mass per charge. 170 m per z. Questions so far? Is this the only way that a cation hits the detector and registers as 170? Well, no. First of all, it could have been any of these pi bonds as well. But also, we can take an electron from a lone pair. I'm abbreviating it there as LP. Now, in this molecule, the only lone pair I have is on bromine. But nitrogens, they have lone pairs. Oxygens, they have lone pairs. All of our other halogens, lone pairs. Those are all fair game. In this molecule, we'll look at how bromine can go from having 3 lone pairs to a radical electron and a hole, a positive charge left behind by 1 electron that was removed. Is this molecule just a cation? It's another radical cation. The molecular ion is a radical cation.
What's the difference between a regular cation and a radical?
regular cation won't have an unpaired lone electron. We'll look at those with our daughter ions next. What's the mass for this ion? Where will it register on the mass spectrum? The signal will be 170 m per z. It is the same ion formed differently.
Doesn't it have less hydrogens in it?
No? Carly?
So just to like clarify, so bromine has 3 lone pairs, so you just took one of the lone pairs and you put the radical atom positive charge on.
Well, I didn't put a radical. I left one of the electrons from one of the lone pairs.
Oh, okay, so it just takes one.
Yeah, it had 3 lone pairs. One of those electrons was removed. One of those electrons stayed behind.
So that's an electron on the oh, okay.
Radicals
Radicals.
Radicals are electrons. Good. How many of you learned a lot about radicals in the past? Yeah, it's interesting how little they come up until organic chemistry. I never realized that until I started teaching general chemistry and realized it's not really in the curriculum anywhere to talk about a radical.
So since like, I mean, isn't every atom in an odd column gonna have a radical on it?
You are suggesting,
But it will be an ion because that's the base.
you're suggesting the free atoms.
Yeah.
But even carbon as a free atom might not necessarily have a radical, or just one radical, but potentially 4 radicals from its 4 unpaired electrons. Or maybe 2 of its electrons are paired in the s orbital, 2 of its electrons are unpaired in the p orbitals. I wouldn't think much about free atoms.
There's never really.
There will be a few instances where we generate like a bromine radical, which I guess would be similar to a free bromine atom. Not a lot of them though. And we'll never generate a free oxygen radical or like a free oxygen atom or a free carbon atom. It'll always be bonded in some way.
And the formal charge will still match the charge of the cation, of the radical cation. Right?
Well, radicals almost never have a charge. Sometimes.
The radical cation.
The radical cation will always be a positive charge. Well, I mean, that's actually getting too specific. There's a lot else that goes on in here that we do not need to get into. For instance, what if the electron beam knocks out 2 electrons? Or what if 2 of these radical or cation species run into each other after they form, and they cause rearrangements to occur and new bonds to form and other bonds to break? It gets very in-depth. We're keeping it surface level. But almost always, the radical is not charged. This is a very rare instance of a radical atom that is charged. Notice that this radical atom, neutral. This cation, not a radical.
So is the whole molecule considered the radical, or is it just the bromine? Or is it the electron that comes off? Like what is the radical?
The radical is an unpaired electron.
That's still connected to the bromine, or the one that's separated?
Oh, good question. No, a radical would be connected to an atom.
Okay.
Yeah, so the electron that gets blasted off.
Gets sucked into the waste.
Yeah, I think it gets removed before the waste.
Okay. Then what is the waste?
The waste is, we're going to get to it. Anything that's just a radical and not a cation gets sucked out. These radicals are also cations. But what you're asking about, is the bromine the radical and the cation? Is the whole molecule the radical and the cation? Both. This is a particle. This molecule is now considered a charged particle and a radical particle. The charge here is specifically at the bromine, and the radical here is specifically at the bromine. but technically both are true.
So, I mean, do the electrons only have a negative charge if it's in a pair? Because like, I mean, or would it have like, or would a radical have like half a charge then?
No, electrons are negative particles. They have a -1 charge. The reason that this radical is not maybe demonstrating a charge is because it is balanced by the protons that are in the structure.
So like on that, on the first one you drew with the radical on, yeah, on the other carbon. It's almost like we're treating the lone electron as if it has no charge at all. It feels like.
I mean, it feels like we're treating these atoms like they have no charge at all. And aren't those atoms just bundles of protons and neutrons? Aren't those positive charges? A nucleus is a positively charged particle. A hydrogen nucleus is a +1. A carbon nucleus is a +6 charged particle. But every time I draw carbon, I don't seem to indicate that it's a +6.
So does the radical on that one carbon not affect its charge at all?
That's correct. Here's what I would say. Why do I have no charges here?
It's balanced.
There's an equal number of negatively charged particles and positively charged particles. We're only showing valence electrons, right? If you counted the number of protons that make up the nuclei in this molecule, and then counted the number of electrons that we show, there would be way more protons than electrons. That's because we only look at valence electrons. But if we looked at all of the protons and all of the electrons, they would be balanced. Now imagine just taking out one electron. It's going to leave you unbalanced. You remove one negative charge, you're going to leave behind one positive charge. This electron is balancing this atom. I mean, these electrons, we're not showing these electrons as negative, but we know electrons are. These electrons are balancing this atom. This electron is balancing this atom. This carbon doesn't have enough electrons to balance it. These are good questions, guys. I'm not trying to stop you because I don't want these to feel foreign to you.
So that carbon with the radical still has, it's bonded to two other carbons and one hydrogen, and it has a radical.
That's right. So the formal charge then is the valence electrons 4 minus 3 plus 1. 3 dots. Or sorry, 3 bonds, 1 dot. 4 minus 4 is 0. Neutral. Could do the same thing here. Formal charge on bromine, it has 7 valence electrons minus 1 bond and 1, 2, 3, 4, 5 dots. 7 minus 6 plus 1.
So I guess I'm kind of looking at it as, in that when you break that double bond, one carbon keeps its half.
Yes.
Okay.
Yep. That is the hardest thing. So when you take a double bond and break it, one atom keeps the lone pair, one atom keeps the remaining electron, one atom loses both of its electrons. Okay. There is one other way that we can remove an electron. What do you suppose it would be? If not from a pi bond, if not from a lone pair, where else can I rip out an electron? Sigma bonds. So if we remove electrons from a sigma bond, I think you would agree that there are a lot of places that this can happen as well. I'm going to focus on one place. I'm going to look at the bond between carbon and bromine. And to do this, I'm going to expand from bond line a little bit. I'm going to show a CH2 and the Br. I'm removing one electron from the 2 electron pair. That means that there will be a radical between the 2 carbons, or between the 2 atoms, and net positive, because one negatively charged particle has been removed. we say that sigma bonds, covalent bonds, are 2 electron bonds. How many electrons in this bond? 1. That's a 1 electron covalent bond. How stable do you think that is? Not very stable. 1 electron covalent bond. Not very stable. It can form. It does form. It's not very stable. Scientists last year reported for the very first time a stable structure isolated in a crystal form with a carbon-carbon 1 electron covalent bond. I mean, that is breaking edge science. No one has ever isolated a crystalline solid that had a carbon-carbon 1 electron covalent bond. So maybe in 10 years when I'm teaching this, I'm going to stop saying this. We've found ways to analyze it. But for now, 1 electron covalent bonds are not very common.
Why doesn't it just completely separate? Like, why doesn't it just break the bond completely and have one take on the radical one?
Good question, Maddie. And this is what leads us to daughter ions. I'm going to say daughter ion signals. These form when groups are cleaved into a radical and a cation. Well, that looks bad. Now, why do we call them daughter ions? Why aren't they sun ions?
Oh, because girls are better.
Touche. I fear that's not the case, considering a lot of this was developed by men. I don't think that's why they chose it, is what I mean to say. Not
Women are not that.
They could have made it gender neutral and called it children ions.
It was not kind of a thing.
They don't call it mother ion, they call it the molecular ion, not the mother ion.
But
They call it
biologists-
chromosomal sisters in biology.
And the daughter cells.
Daughter cells.
I think it's due to like cells asexually reproducing. They call the first one the mother.
But it's
Right.
interesting, right? To make the feminization of
Reproduction.
science. Yeah. There's even a feminization in like cities. Cities are always referred to as she's, her. Sister cities, sister ships. Did you say ships?
Ships. Are
Yeah. Interesting. Anyways, they're called daughter ions. Oftentimes, these cleave in a way that we call alpha cleavage. So you can identify a functional group and you will cleave that functional group off of the molecule. Whether that functional group prefers to take the positive charge or whether that functional group prefers to take the radical depends on the functional group. But a lot of times you can look towards a functional group, cleave the position alpha to it, the position just off from it, and you can predict a daughter ion. In this case, with benzyl bromide, there are 2 very prevalent daughter ions that we could predict. Doesn't mean that they're all going to form to an equal extent, but there's two that we could predict. One of them in green will do the same bond that we looked at before. I'm showing this as kind of cutting this CBr bond. We said that one electron can be removed from it and it can stay as a one electron covalent bond, but that's not very stable. So then the question becomes, how will they split? And the answer is there are two ways. We have to consider both of them. I'm showing them the CH2 and the Br further away from each other now. They're not meant to be sharing an electron anymore. In one instance, the lone electron might be taken by the carbon, and the positive charge ends up on the bromine. Now, this radical fragment is not affected by the magnetic field. It's pulled into the waste. And this cation is pulled into the magnetic field and hits the detector. What signal would it produce if this hit the detector? That's right, 79. I think what I'm going to say is and or, because it's both, but it depends on which one is there. Oh, I forgot my units, which is M per Z. Would you agree that the other possibility is likely as well, that the bromine takes the unpaired electron and the carbon takes on a positive charge? Bromine is now a radical and neutral. That's a free atom, technically. That's a free atom bromine.
That bromine then ionically bond, like just in our one other node.
Well, it can't ionically bond because the bromine's not an ion. But these ions, you wouldn't see them ionically bond. I think everything that gets pulled into the waste, you might see some like side reactions between things in there. But remember, this is a very small number of molecules, so it's
Does that radical act independently of the destroy free atom?
free atoms aren't very common.
Like, I mean, well,
The only free atoms that I can think of would be like in a star or in a supernova. But on Earth, there are much fewer free atoms. Of our common elements, carbon, never a free atom. Oxygen, never a free atom. Halogens, usually not free atoms, except for here. Now, what mass would this fragment show up with on the spectrum? 91. Yeah, we said earlier 7 times 12 was 84, 7 hydrogens, 91. So this has a signal of 91 mass per charge. I wonder if I should have told you guys, this is 170 and 172, but you're only ever going to see 170. And I know I forgot to tell you that this guy also forms that signal at 170. And then technically it also forms it at 172. This fragment is not these two fragments.
So the chunks that have the radical, those go to waste, is that what you said?
Yep. This will not hit the detector. This will not hit the detector.
And the signal is just you combining the masses, is that right?
You add up the mass.
Yeah.
Yep, that's it. You look at the fragment that has the positive charge, whether that's the whole molecule or just a daughter fragment,
Okay.
and you add up the mass.
Okay.
We could add this up differently as well. We could have added CH, 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 C, CH2. Could have done it in sections if we wanted to. There's a lot. This is why people like to bring a calculator, because they think they're going to have to do this like math on fragments.
So technically you could just find the signal just from the chemical formula? Like from the mass of that?
Yeah. Mm-hmm. And in an ideal world, you could go backwards. You could get the signal and derive the chemical formula. But sometimes there are multiple chemical formulas that have the same molecular mass. So you wouldn't be able to be confident.
Yeah.
There's another place that we could cleave for like an alpha cleavage that would give us a different set of ions. That would be cleaving next to this aromatic ring. So here's what I'd like you guys to do. Predict the two sets of fragments that could form and the mass to charge signals that they would produce. I recommend doing it like I did before. Draw two sets of the same thing and then just assign the radical and the cation to the different fragments.
Brooklyn's bonded to the carbon.
It will be, yep.
I can call them either CH2 or H2.
Correct. Yep, all would be the same.
Train outside. Oh, that's really.
Do you think you're done?
Oh, with my drawing.
I got the hose.
I know you did. That's why I was confused. Nice, bro. Good work. Good.
We've got too many carbons here. It's a little awkward to draw it without the. No, and we're not doing anything within the.
Oh, that's what I was thinking.
But you've got your positive charge in this and you don't have a radical in there. So here, positive on one side, radical on the other. We don't have a CH3. We have a CH2. Oh, that's fair. That's fair. But look back at the bond line. CH2 beyond.
This is not. This is not. Just a dot. Yeah, it's an electron.
And you're off to a good start. Well, actually, we want to break that bond between the two carbons.
Yep.
And then the carbon-bromine bond won't be broken.
Good. Now, I would say they're drawn a little close together, so it makes me worry that you're trying to show something similar to the bottom in there in the last. And so maybe circle one, and like we did up here, show what sigma. That'll help distinguish them. You're off to a good start, yeah. Now the two carbons that broke their bond, they're going to swap having the radical and the opposite charge. One takes the radical, one takes the positive. You're off to the right start. Now do that again. And the two carbons that broke their bond, one will keep a radical, one will take a positive, and then they'll flip to the other side. Good. Perfect.
I almost drew this.
Yeah. Easy. I'm gonna talk about that. Good work. This does not form a sigma. This one will. And
This one
is
won't.
This one will. This one will. So your masses were just flipped. How you feeling now?
I'm confused.
You have a lot of carbon going on here.
This is just, I'm trying to like visualize it.
Mhm.
It's like breaking this.
What might help is like copy paste it and then just erase that bond.
This whole thing.
No, just this bond, the bond between carbon and carbon. That's the bond that the arrow is over. So just erase that bond twice. And then one time, give the radical to one carbon, the positive to the other, and then flip that on the second set.
Okay, I think I need to like see it more to understand.
Okay. Yeah. Good. Yes, great.
Makes
Well,
sense,
if a
right?
signal, like, you wouldn't count that as a extra hydrogen.
There is no hydrogen there.
Okay.
There was never a hydrogen.
Okay.
Yep.
Okay. So like with the signal, right?
Yes.
Okay.
Yeah.
Yes, those look good.
Okay.
Good work. Nice.
No,
Yep.
there's no bromine on it. So, yeah.
Okay, so
And then you want them to add it up to either 170 or 172.
when breaking this bond, if it helps, what I would recommend is draw the molecule over again. And draw it 2 times, because every time you cleave a sigma bond, there are 2 things that can happen. Identify the bond you want to cleave. I want to cleave the carbon to carbon bond. That's why I've drawn it over the carbon to carbon bond. So I'm going to erase that bond. Now, a lot of you drew this group just like that, and that is not wrong. I don't like it. So I'm just going to rewrite it as CH2Br because I don't know, maybe to me it looks better. But it is not wrong to have it drawn with just that little stick. Now, when one electron is removed from this 2-electron sigma bond, the remaining electron has 2 ways that it can be pulled. The remaining radical can show up with the carbon on the left, or the remaining radical can show up with the carbon on the right. Same bond breaking, 2 ways the radical shows up. And the positive charge shows up in the other place. Which of these 2 fragments, left or right, radical or cation, hits the detector and produces a signal. The fragment on the right, the cation. And that's going to have a mass of 12 plus 2, 14, plus 79 or 81. So you guys gave it to me earlier, because if I had to do it in my head, it would be really hard. That's 93 and or 95. Mass per charge. If the positive charge formed on my aromatic ring carbon six times 12, there's 6 carbons in there. And how many hydrogens? There's 5 hydrogens. So 6 times 12, 72, 5, 77. Mass per charge. All right, so out of these ions that we've generated, molecular ion and these 2 daughter ions from alpha cleavage, let's see what shows up on our mass spectrum. I'm going to try to model a little bit of the mass spectrum over here. Up here at 170 and 172, we have these 2 signals, and that is the molecular ion signal. So I'm going to label that as M+. Down here we have 75, 80, 85, 90, and we've got this huge signal at 91. Matt, you're not sure? Okay. Now we can also label that relative to the molecular ion. We can say that this signal is M minus the mass that has been lost. How much loss has been how much mass has been lost from the molecular ion? 79. The molecular ion weighed 170. This ion weighs 91. That is the molecule less 79 mass units. So we can call it the M minus 79. And if you recognize what has a mass of 79, then that helps indicate to you I've lost bromine by forming this fragment. Bromine weighs 79. And we said up here that the aromatic ring with the CH2 plus, that has a mass of 91. So now we can actually make this prediction. The fragment that we see here is CH2 plus connected to the aromatic ring. Now, let's look for some other things, like, do you see a signal at 79 and 81? Here's 75, here's 80. No, not really. There are little bumps that come off there. So out of the 500 million molecules that are being disintegrated and hitting our detector, maybe a handful of them are kicking off bromine cation and hitting here, but this is not a significant peak. This doesn't form often. So we can make predictions about how a molecule might cleave, but that doesn't mean that all of them form equally. This forms very often. This does not form very often. We've got these signals at 93, and 95. Here was 91, 92. I have no signals at 93 or 95. So just because we can predict that this can form doesn't mean it likes to form. And then we've got this last predicted signal at 77. Here's 75, 6, 7, nothing there. So there's a lot of ways that benzyl bromide can cleave. It doesn't readily cleave in all of them. So this idea that you are shooting a gun at the molecule and that gun is picking away electrons, not all electrons leave to the same extent. This electron leaves the most often and in a way where the carbon takes the positive charge. But wouldn't you agree that that makes more sense for carbon to take the positive anyway? Bromine, a little bit more electronegative, takes the radical electron, leaves bromine less electronegative, or carbon less electronegative with the positive charge. Okay. Good stuff, right? There's one more name that is often given to some of these signals, and that is the term base peak. I don't know what base peak might mean to you. I don't necessarily like that name in general, but this is the most abundant signal. It has the largest relative intensity. It's the fragment that forms the most. Sometimes this is the molecular ion. Oftentimes it's a daughter ion that forms the base peak. And in a way, this can actually tell you something about stability of the molecule. The fact that this cation forms the most often tells me that this cation is the most stable. It's the easiest to form, it forms the most readily. And that's usually because it's stabilized somehow. This is actually stabilized by resonance. There are a 3-atom system containing a pi bond and a charge. So this positive charge is delocalized throughout the entire ring by resonance. That stabilizes a charge. That makes it easier to form. I want to do some practice with you guys, but I need you to get up and get your blood flowing and get your brains going again. So let's take a short 5-minute break and we'll come back in and look at some more practice problems.
What's the other, there's like 2 other lines that look somewhat abundant.
I know. Well, we can try to work backwards. So here's 50, 45, 40, 39. So is there a way that I can get a fragment of this molecule that weighs 39? Well, it definitely doesn't have bromine. And a mass of 39 would be, well, we could try to get there from carbon as much as possible. So 12 times 3 is 36 plus 3 hydrogens. So if I had 3 carbons with 3 hydrogens and a positive charge, that would form that signal. That could be half of the ring. How does that form? Don't worry about it.
So we're mostly concerned with the molecular ion and then the base.
That's right.
Okay.
Yep. To be fair, on things like the unit test and the, on the unit test, mainly I would say predict a molecular ion. I think you guys would agree the molecular ion is easier to predict than a daughter ion. Don't break any bonds. Just pull out 1 electron. That's actually pretty easy. The daughter ions, you have to do more like investigative searching.
And when you're saying predict the molecular ion, it would be like predicting those three, like the three possible areas we could pull an electron from.
Sorry, I was just thinking that this little thing I showed, it might also be a radical. I think that is a radical cation. I didn't want to tell you guys that there are other fragments that can be radical cations because that's getting too deep. In our class, the only radical cation will be the molecular ion. And because I was thinking that, I missed what you said.
So you had said on the unit test,
Oh.
you might ask us.
I locked everybody out.
Carly's gonna have a very good Sorry, Maddie.
But then I changed it so it kind of the increase.
I don't think use francium in this class.
Tell me why you want to use francium.
I remember looking at like liquid substance. If you could stabilize it, it would be like the perfect alkaline.
What does perfect mean?
It would be used for warfare.
It was a long scale. And that was, yeah, that's perfect, all right.
Yeah.
Your perfect alkaline metal is
War.
war?
That's all it's.
Well, for that reason, it doesn't really apply to our course content. Maybe if I was teaching the organic chemistry of war, I might try to incorporate francium into it more.
Okay.
I mean, actually, organic chemistry does apply to war. Did it not unlock?
Yeah, well, you get
You're getting your exercise. Maybe that's how I
I think that might be, yeah, just because I need to compare it easier.
I see it.
Yeah.
It's- Okay. Weird. So francium is a group 2 metal?
One.
Oh, an alkali metal.
It would be the most so electropositive.
Yep. Why does that make it good for warfare?
Well, I mean, it would explode in water.
Whatever you want to call it.
Would it?
Yeah, I think so. Ask ChatGPT.
He said the one difference is.
I think the larger your group 1 metal gets, the less reactive it becomes. It requires very little energy to take away its valence electron.
I guess you're right.
That's because it's in a very far shell and there's a lot of shielding going on. Maddie, you had a... Oh, sorry. I didn't get to
Yes, sorry.
answer your question.
You said on the unit test you might ask, like, what's the possible molecular ion? So, would, like, or something like that. So
Yeah.
when
Here's a
you
molecule.
say it could break in these 3 areas.
You just have to come up with one of those 3 ways.
Oh, okay.
Yep.
Okay. So if you just show the one where it's coming from the sigma bond.
And I'll have you guys do an example like that here in a minute. Yeah.
Wouldn't it like if it's more electropositive, wouldn't it be more unstable, meaning more higher energy?
It is a higher.
Because I mean, if it's more electropositive than sodium, it would take much less for it to violently react.
Yeah. No, I don't know about that.
I mean, do they get more explosive as you go down the group 1? Or they get less?
They don't. They get less explosive.
Yeah.
I mean, lithium, sodium, and potassium all fairly explosive. I don't think you'd want to deal with any of them in a lake.
What about like cesium?
I think it's less so explosive. Not non-explosive, but less so. All right, we can come back to this, yeah. All right, before we do some practice problems, I want to put a name towards something that we already looked at, which is isotopic clusters. I keep spelling prevalent wrong. I think that's right, but if you guys know better than me, let me know. There's two species that these are most common to see. An isotopic cluster is a cluster of signals that form from different isotopes being present. Chlorine 35 and chlorine 37, we say that this has a 3-to-1 isotopic cluster, and that's because chlorine 35 makes up 75% of all chlorine. Chlorine 37 makes up 25%. So whenever a daughter ion has a chlorine attached, you see this 3-to-1 ratio. Let's say that this is the M+ ion, the molecular ion. Then this next one could be called M+2. And it's that 2 mass units difference that helps you identify an isotopic cluster. There are some clusters in here that are 1 mass unit away. There's even this little cluster here around 60 that has a mass unit 2, or a signal 2 mass units away, but it's not 3-to-1 in the correct direction. Also, we know that benzyl bromide doesn't have chlorine. This is not the best isotopic cluster in my opinion. The 3-to-1 signal is hard to spot, and there's a lot of noise and a lot of other stuff that we're not trying to analyze in here. What works better is the bromine cluster. Bromine 79 and bromine 81. Bromine 79 makes up 51%, bromine 89, 49%. Almost a 1-to-1 cluster. That's your M+ and your M+2. The bromine isotopic cluster is super nice. Anytime it's there, it's pretty obvious to see. But because bromine likes to leave with the radical, you don't always see a lot of signals that have bromine's 1-to-1 cluster. Where's the 1-to-1 cluster present on the mass spectrum for benzyl bromide? Yeah, here at 170 and 172. Anywhere else? No, because none of these other fragments kept bromine.
Does the more electronegative atom take the radical with it, or does it just kind of ignore it?
Very often, the more electronegative atom takes the radical, but not always.
I'm sorry if this takes us back a little bit, but I think I'm not really understanding what the relative intensity is and what the numbers are relative to.
That's okay. I'm glad you asked that. Don't look at it. Yeah, the numbers are not meaningful. It's relative, meaning it's been normalized to this spectrum. So the tallest peak is set to 100.
Okay.
Everything else is relative to that. I like to think of it as abundance.
Is it like a percentage of 100?
Well, it can't be because the tallest signal is at 100, but the tallest signal isn't 100% of all of the signals, you know? In this case, I would say that tallest signal is 90% of all the signals that were detected, but not 100%. I don't like that, but they do clarify it by calling it relative intensity. The fact of the matter is, you do this one time with benzyl bromide, you do it a second time, you do it a third time. Your instrument is going to say, this is how many hits I got. I got 300 million molecules with that daughter ion. The next time, I got 450 million molecules with that daughter ion. But the proportions are always the same. So rather than saying, how many hits did I get on this run, I'm just going to make it relative and say, that's my tallest peak. Relative to that, this is where everything else is. Yeah. This acts like a fingerprint, so that I run it on one instrument, you run it on another, and we get a different number of hits on our detector. The proportions are a fingerprint to benzyl bromide. All right, let's look at some other molecules and predict whether we can use alpha cleavage to find a base peak, and if we can determine one possibility for their molecular ion signal. I've got a lot of students this semester that are using propofol for their compound. Oh, bummer. Propofol has the chemical formula C6, plus it's got 2 isopropyl groups. That's 6 again. So C12. Man, I'm just going to Google it. Propofol chemical formula. C12H18O. H18O. I'm going to go down here to the search. Oh, 2,5-diisopropyl phenol. Yeah, that's what I'm looking for. No mass spec. All right, well, 2,6-diisopropyl phenol. No, actually, that's what I'm looking for. That's propofol. For those of you that know propofol, it's got the 2 isopropyl groups opposite of the alcohol group. So here's its mass spectrum. What is the molecular mass of propofol? Don't look at the thing. Look at the graph. According to the mass spectrum, what is the mass of propofol? Are you looking at this one?
Oh, yeah, is that not?
We should go to the highest mass signal.
Oh, okay.
And these dots go by 2. So here's 160, here's 170, here's 180. 178. And if we just scroll up, that's why I had to hide that so quick, it tells us right there, mass of the molecular ion, 178. Now, I think you guys would agree that signal at 178 is not the highest mass signal on the spectrum. This tiny little one down here is. Now, when I give you a spectrum, it will have numbers labeled so that you don't have to guess what the signals are that are meaningful. This is essentially an isotopic cluster. 1.1% of the time, carbon weighs 13 instead of 12. And there are 12 carbons here, so there's a good chance that you have a bunch of different molecules that have a heavy carbon. And 0.1% of the time, hydrogen weighs 2. So all of those instances adding up gives me this possibility for a signal here. That's how I would justify it to you. So we're looking at propofol, which has a molecular weight of 170 because the molecular ion shows up at, a molecular weight of 178 because the molecular ion, highest signal in the spectrum shows up at 178. Can we propose a plausible molecular ion for propofol? Anybody brave enough to come and show us?
What'd you say?
Propose a molecular ion for propofol. Yeah, I'll give you this red one. Yeah? Rowan, I will say, you should show your radical as well. I know that that's not an explicit rule we said earlier in the semester. We said we can assume all lone pairs, but we never really said we can assume radicals. I'd like for you guys to show your radicals when you draw a radical cation. Good. Good work, Jamie.
Look.
Yeah.
Previous example.
For sure. Let's talk about Jamie's. Any disagreements? Any concerns?
Can I ask a question?
Yeah.
Where does the double bond go? Is that like what gets like ejected, or is
What is a double bond?
it's sharing twice? Well, it's
Yeah.
sharing electrons.
Yeah, so there's a sigma bond and there's a pi bond. So a double bond is 4 electrons.
Yeah.
But when we break a double bond, good work. Yep. When we break a double bond, we're not breaking the sigma bond, we're only breaking the pi bond. So we're really looking at 2 electrons. And then the electron beam in the instrument is that BB gun that picks off one of those pi electrons. So one of them leaves, one of them stays. One carbon loses both electrons. One carbon only loses one. Yeah? If it helps, you could say, I'm going to not draw it as a dot, but not going to draw the bond as a line, but I'm going to show the bond as the 2 electrons. And then get rid of one.
Oh, okay. Thank you.
Yep. What do you guys think about Rowan's? Good? Yeah, definitely. He took a lone pair electron rather than a pi bonding electron. Both of these are plausible ways for this molecular ion to show up. There are a number of other plausible ways. Anywhere that there is a sigma bond, you could pull out 1 electron and then show those atoms held together by a 1 electron covalent bond with a positive charge. The least likely to occur, though. What do you think has to form, or what do you think has to be lost to form this base peak? What is the signal of my base peak? What is the mass to charge signal? Yeah, 160, 162, it's halfway between 62 and 63, or 64. 163 mass per charge. In other words, the base peak is m minus what? 15. From 178 to 163, how much mass has been lost? 15. What weighs 15? No. Oxygen weighs 16. Hydrogen weighs 1, so together they weigh 17.
Oh, that's
A CH3 group. A methyl group weighs 15. 1 carbon, 3 hydrogens, 12 and 3. Where do you think I lose a methyl group from propofol? Anywhere. So, what is a possibility for this base peak to look like? Well, the alcohol is still present. one of the isopropyl groups is still present, but the other isopropyl group is going to lose one of its methyls. So there's going to be a CH3 byproduct here. What charge, or where does the charge go? Where does the radical go? I need this whole thing, this mass of 163, to hit the detector. That piece gets a positive charge. I need this methyl group to leave and not show up. Methyl gets a radical. Is there a possibility that the methyl group takes the charge and puts the radical there? Always. But how often does a mass of 15 show up? Almost never. So the CH3 plus can form, it doesn't really. This is the structure of your base peak. This is your M minus 15 fragment. All right, before I send you guys on your way, quick direction. If you look at this correlation table document, the front page is mostly for IR, which we're going to start looking at tomorrow. But the second page has a brief overview of common things in NMR and mass spec. So here are some common masses that we see. I do have a typo. This benzyl group that we looked at earlier has a mass of 91, not a mass of 92. If I can make that change, I'll try to do it sooner than later. But this is not comprehensive, it's selective. You will notice that different fragments, I don't know why it's so blurry, different fragments can have the exact same mass. So just because you see a mass on the spectrum doesn't mean you know what fragment you see, but these are very common patterns of fragments in our molecules. All right, guys, we'll look more at IR tomorrow. Have a good night.
Thank you.
You're welcome.